So I specialize in approximation theory, and this talk will be related to certain problems which are the very heart of the approximation theory. Density means when you are trying to approximate functions by something simple like polynomials. So that's the notion of density. The last 10-15 years I was kind of obsessed with doing these things in multivariate. I still remember when I was a student, actually I did my undergraduate in Moscow, and my advisor there kept telling me when I graduate, you have to go to multivariates, forget univariate polynomials. So in the last 15-20 years I was trying to do multivariate polynomials. And the beauty of approximating in several variables is that it's basically an analytic problem, so you use lots of analysis, but since you are doing it in several variables, the domains become much more interesting, and the geometry of the domain starts affecting the results that you are getting. In one variable, it's basically the interval, so there is not too many things you can do there, but in several variables, it gets a little bit more exciting. So it all started with the Weierstrass theorem, which you might have heard about. So Weierstrass approximation theorem says that you take any function which is continuous on the interval a, b, take any positive epsilon. There is always a polynomial of some degree k which will deviate from your function by at most epsilon. The deviation is measured in this maximum norm or supremum norm. Basically, this theorem was the starting point of approximation theory. And this is the algebraic version, and there is a trigonometric version of the Weierstrass theorem when your function is supposed to be not just continuous, but also periodic and negative pi pi. Periodic means that the value at negative pi and pi is the same. And instead of approximating by algebraic polynomial, you approximate by trig polynomial, which is a linear combination of sines and cosines. And then the statement is pretty much the same. Given any epsilon, you can find a trig polynomial of some degree, which deviates from your continuous periodic function by at most epsilon. So that means that both algebraic polynomials and the trig polynomials, they are dense. So that's the meaning of density. You can, given any small error epsilon, you can approximate your function up to this error epsilon. Actually, I read somewhere that Weierstrass was 70 years old when he proved this theorem, which is kind of a good prospect for me. I'm going to turn 60 this year, so still have a little bit of time. And actually, when he was 50 years old, he proved his famous example showing that there exists a continuous function which is nowhere differentiable, which you probably also heard about. And I read somewhere in some survey paper that many people were kind of very much annoyed by this example that he did when he was 50. So when Hermite wrote a letter to Steele TS, he called it lamentable plague. He was so annoyed by the fact that such bad functions exist. So somebody wrote it a while later that Weierstrass, he committed this crime against mathematical community when he was 50, that he constructed this terrible example. But then 20 years later, he kind of fixed his crime because he showed that, okay, there exist functions which are very bad, very non-smooth, but at least we can approximate them arbitrarily well by smooth functions. So this was kind of a positive happening after a very negative happening. And a little bit later came a generalization which was given by a French mathematician by name Picard, and he generalized Weierstrass's theorem to polynomials of several variables. So instead of now we're going to several variables, so we take a compact k in the d-dimensional space. Now my functions are real continuous functions on this compact k, and the norm is the usual sup norm again. And instead of considering polynomials of one variable, we consider polynomials of d variables, total degree at most n. So these are linear combinations of monomials x to the k, where x to the k now is the this notation, x is a vector which has d coordinates, and you raise the first coordinate in the power k1, the d's coordinate in the power kd, and that's your monomial here. And mod k denotes the sum of coordinates of this integer vector k. And when you take mod k to be at most n, that means you are considering algebraic polynomials of degree at most n. So what Picard did, he proved that even in this generality, if you take functions, several variables, and in compact k, you can approximate by polynomials in d variables. So now instead of writing this epsilon stuff, I'm just saying that the closure, PD denotes all polynomials. If you take the closure of all polynomials, you get, well, but meaning the closure here means in this norm, of course. So you take the closure in that topology. Then you get all continuous functions on the compact K. Now that sounds like a very strong generalization of the original Weierstrass theorem, but it turned out that there is a topological approach to this problem which was given by somebody by name Stone, and all the previous statements that I had so far, they follow very easily from this theorem which was found by Stone. So here is what Stone did. He said, let's take A to be any subalgebra of CK, continuous functions in the compact K. What does it mean, subalgebra? It's a linear space, but you're allowed to multiply your functions. So if you multiply any two elements of your subalgebra, the product is still in subalgebra. So your subalgebra is closed relative to multiplication and summation. And in addition, you need two properties of this subalgebra. Your subalgebra has to separate points in K, which means given any two distinct points in K, you can find an element in your subalgebra which takes distinct values at these 2 points. So your subalgebra separates points. One condition. Second condition, the subalgebra has no zero set, which means no matter what point you pick in your compact set, there is always an element in your subalgebra which doesn't vanish there. So you cannot have points on compact where every element of your subalgebra vanishes. So if these two conditions are satisfied, then the closure of your subalgebra is going to be all of CK. So your subalgebra is going to be dense in C of K. Now, very easy to check that algebraic polynomials, trig polynomials, polynomials of several variables, they're all subalgebras. You can multiply polynomials, you can sum them up. And these properties of separating points and no zero points, they are satisfied by polynomials as well. So whatever we mentioned before, the Weierstrass theorem, Picard theorem, they all follow from the Stone theorem. And nowadays, this is called the Stone-Weierstrass theorem. Actually, there are many variations of the Stone-Weierstrass theorem. In a way, this is not the strongest form. I have one more form here present, which is a little bit more general, and sometimes it's very useful. The only property that we are dropping now is the second property, that A has no zero set. So I'm looking at the situation when A may have a zero set, your subalgebra. So I'm still looking at a subalgebra in CK. It still separates points. So the first condition I keep. But the second condition I drop now. So I assume that there is a certain set ZA, which is the zero set of your subalgebra. Every element of your subalgebra vanishes on that set 0 sub A. And then it turns out that your subalgebra is going to be dense exactly in the set of those continuous functions which also vanish on that set, which is pretty natural. So if you take functions which vanish on the same set where your subalgebra vanishes, you still have density in the set of this smaller space of functions. Very useful result. Very often it is used as well. Okay. So here is a question which many people considered. If you can approximate every continuous function by polynomials. But when you say you approximate by polynomials, you take linear combinations of all powers of x. So all monomials are used in general in this Weierstrass theorem. Can you get away by using not everything, but a smaller set? Well, here is a very simple example. If I fixed any vector r with positive integer coefficients. So r is a fixed vector, and I looked at the monomials of this form, x to the power inner product of r times k is any integer. So now I'm not looking at all monomials x to the k, but monomials of some special structure, because r is some fixed integer vector. And it's very easy to check. It's a routine exercise that if you take the linear span of all these monomials, you will have a subalgebra which satisfies all the properties of the Weierstrass theorem. When you multiply any monomials of this form, you get again a monomial of this form. When you add them up, it still works. So it's a very simple example of how this Weierstrass theorem can be applied. So you get density. Of course, the exciting problems are the ones where the Weierstrass theorem does not work, because if you can check the subalgebra property, and it's not too exciting. So the interesting questions are exactly those questions when you are not dealing with the subalgebra. And usually what happens, you take a set of polynomials where either summation breaks down or multiplication breaks down. So one of the two operations that define the subalgebra. So here is an example. It's a very famous theorem by Münz. One variable. You take the span of monomials x to the power lambda k. Lambda k's are some positive integers. Start with 0, and then they increase. Question is this set going to be dense in the space of continuous functions on 0, 1? Not. And the beautiful answer is given by the Münz theorem, which says that the span of this lacunary power x to the lambda k is going to be dense in C0, 1 if and only if the sum of the reciprocals of 1 over lambda k is infinite. Necessary and sufficient condition. Beautiful solution. Now, what does this condition mean? It means, of course, that lambda k cannot tend to infinity too fast, because if they tend to infinity very fast, your series is going to be convergent. So it is a certain increase property that is involved here, which tells you that lambda k's can increase to infinity, but not too fast. Now, for instance, if you take lambda k's to be prime numbers, the known results about the density of prime numbers say that for the prime numbers, the sum of the reciprocals is infinite. So you can, for instance, just take the monomials whose exponents are prime numbers, and that will suffice for approximating. So that's already enough, even though prime numbers are, well, they're not that dense, but still that's good enough. But if you take lambda k's to be perfect squares, k squared, of course, sum of 1 over k squared is a convergent series. So then by the Münz theorem, you don't get density. So this is now, this sequence has two large gaps, and that doesn't allow density anymore. Now, why couldn't we use the Weierstrass theorem in this example? Well, I am taking a linear span of some monomials. So, of course, this is a linear space. But what happens if I multiply two polynomials like this? They are not going to have the same structure, right? And that's an example when you don't have a subalgebra anymore, the solution becomes non-trivial. You have to put a certain condition on this space, like this condition here, in order to get density. And here's another example, which is somewhat different from the Münz theorem, but it's also very nice. I look at the so-called theta incomplete polynomials. What does it mean? I fix a number theta between 0 and 1, and a theta incomplete polynomial is a span of monomials x to the k when k varies between theta n and n. So basically, I delete the first theta n powers, they're out, and keep only the powers starting with theta n. To make it a little bit more, so a polynomial has these powers, somewhere here. Well, this doesn't have to be an integer, but I'm lazy to write integer part, doesn't matter. So you drop this part. This is out. And then you use only the rest. Of course, if you truncate a polynomial like this, it's going to have many zeros at the origin, right? It not only vanishes at the origin, but many derivatives will vanish at the origin. So a polynomial, which is a linear combination of the remaining powers, it will have many zeros here, and then it can do something else, of course. So it will touch axis x at the origin with a high degree. So you don't expect to be able to approximate every continuous function by polynomials like this. And it turns out that there is a beautiful solution to this question as well. What can we approximate by theta incomplete polynomials? The answer is that if you take a function which is continuous on -1, 1, it is a uniform limit of theta incomplete polynomials if and only if your function vanishes on the interval -theta, theta. So in order to approximate by this theta incomplete polynomials, your function has to be 0 on this smaller interval. Then it doesn't matter what it does. Then you will be able to approximate on the whole interval. Now again, can we use the Weierstrass theorem to study this problem? You have to notice that it's actually interesting. If you take two theta incomplete polynomials and you multiply them, it's still a theta incomplete polynomial. It's very easy to check. So this set of polynomials is closed relative to multiplication. But how about if you add two of them? The sum is not necessarily a theta incomplete polynomials. So linearity breaks down. That's why Weierstrass theorem is not applicable. Actually, there is a much deeper theory behind this example. When you look at the general weighted polynomials of this form, you have a fixed weight omega. It's a fixed function. I call it a weight. You raise it to the power n, and you multiply it by a polynomial of degree n. You have to notice the same n, polynomial of degree n, and a fixed weight to the power n. My theta incomplete polynomial looks like that, with weight being a power of x, some weight. So it turns out that whenever you approximate by weighted polynomial of this form, the answer is going to be that you can approximate functions assuming that, well, you will be able to approximate functions not on the whole domain, but on a smaller domain, like here, not all domain, but smaller domain. And this smaller domain is controlled by your weight. Here is another example of this happening. I take the weight to be the Gaussian weight, e to the negative x squared. So with this weight, e to the negative x squared, I look at the weighted polynomials. So this weight is raised to the power n times the polynomial of degree n. Of course, this weight very quickly converges to 0 at infinity, positive infinity, negative infinity. So now, these polynomials are good on the whole real line. I don't have to necessarily approximate on the finite interval. I can approximate on the whole real line. The question is, what can I approximate by these weighted polynomials with the Gaussian weight? Which functions on the whole real line can be approximated? And the answer is, again, very nice. You have a function which is continuous on the whole real line. It is a uniform limit of these weighted polynomials with the Gaussian weight, if and only if the function is 0 everywhere outside interval -1, 1. So it can be anything you want on -1, 1. Outside it has to be 0. Now these last two examples, they correspond to the situation when you are not dealing with subalgebra. Your set of functions is close relative to multiplication, but not addition. So addition breaks down. Okay, now I come to the problem which is the main topic of this talk, basically. I want to look at the homogeneous polynomials. This is a very special class of multivariate polynomials which appears in many areas of analysis. They're very useful, very natural object. What do I mean by a homogeneous polynomial? A homogeneous polynomial of degree n is a linear combination of powers x to the k when the degree k is fixed, is n. When we set polynomials of degree at most n, I would write here mod k is less or equal n. Now I am setting it to be exactly equal to n. So just a simple example. In two variables, let's say, this is a homogeneous polynomial of degree 2, right? Second power of x, again, x to the power 1, y to the power 1, total degree is 2 here, and 2 again. But if I add something like 3x, this is a polynomial of degree at most 2, but it's not homogeneous anymore. So Hn is the set of homogeneous polynomials of degree n, and Hd is the set of all homogeneous polynomials. So it's the union of all homogeneous polynomials. Question, is there a Weierstrass theorem for homogeneous polynomials? Can you replace polynomials in the Weierstrass theorem by homogeneous polynomials? This is the problem I was looking at, let's say, last 10 years. This set, H of homogeneous polynomials, is much smaller than all polynomials. Can we use the Stone-Weierstrass theorem? Is this a subalgebra? Now, if you take two homogeneous polynomials and you multiply them, it's a homogeneous polynomial, still of higher degree, of course, but still homogeneous. How about if you add? No. If you add let's say, this part here is a homogeneous polynomial of degree 2. This part is a homogeneous polynomial of degree 1, and this is 2. You add them, it's not a homogeneous polynomial. So linearity breaks down. That's a problem. So you cannot use this Stone-Weierstrass theorem. So this is one of those exciting problems when something else is going to happen. Okay. Here is a simple observation about homogeneous polynomial. If you look at the homogeneous polynomial along a line, Tx, x is a variable vector, t is a real parameter. So this Tx is a line going through the origin and this point x in the D space. And along a line like this, you can pull out this exponent t to the n from the homogeneous polynomial because of the way the homogeneous polynomials are defined. So they have this very simple property. Hn at Tx equals t to the n times Hn at x. Now that tells you something about the behavior of this homogeneous polynomial. Let's say here is a point x, and my homogeneous polynomial is 1 at this point. Or I have a sequence of homogeneous polynomials which is simply 1 at this point x. What is it going to be at negative x if it's 1 at x? Well, at negative x it will be either 1 as well or negative 1, depending on the parity of n. For even n it will be 1, for odd n it will be negative 1, right? Now, what will happen inside here to my homogeneous polynomial as n goes to infinity? If I have a sequence of homogeneous polynomials which are normalized by 1 at point x. Well, inside here, t is less than 1, right? So t to the n will tend to 0, right? So if I have a sequence of homogeneous polynomials which is 1 here, inside this segment, it will have to go to 0. How about outside this segment? It will have to go there to infinity, right? Because t to the n, when t is bigger than 1, goes to infinity. So what can we approximate by polynomials like this? Looks like along this line, not too much. But what if you have a domain in the D space? What can you approximate by homogeneous polynomials? Well, you can approximate the boundary. Because if you go along any line, and your polynomial tends to your function here and here, then inside it will have to tend to 0. Outside the line, it will have to go to infinity. But at those 2 points, it can be fine. So it kind of leads to the conclusion that if you look at the Weierstrass problem for the homogeneous polynomials, you don't approximate your functions on the whole domain, but on the boundary domain of the domain. That's still a legitimate question. So now the question is, if you have a compact K in the D space, and you look at the boundary, I will denote by this delta K the boundary of the domain. So it's without inside, right, and without outside, just the surface. Can you approximate a continuous function on this surface? That's the natural question to ask. Because you cannot approximate inside, you cannot approximate outside, only on this surface. Okay, so next question is, does the Weierstrass theorem now is going to hold for the homogeneous polynomials on all the surfaces? That's the question to ask. Another observation is that, well, I already mentioned that Stone Weierstrass is not applicable. Here is another very simple but important observation. If you look at a homogeneous polynomial of degree n, and n is even, then it's an even function. Even function in the sense that hnx equals hn negative x when n is even, right? For odd n, it's going to be an odd function. Now, a general continuous function, it doesn't have to be even or odd, right? You can may have a function which is neither even nor odd. So you cannot really approximate a function by a single sequence of homogeneous polynomials, because those are going to be either even or odd. Now, how can you go around this problem? Well, your continuous function doesn't have to be even or odd, but it's very well known that you can always split it to an even function plus an odd function, right? An even function you hope to approximate by even homogeneous polynomials. An odd function you hope to approximate by odd homogeneous polynomials. So the conclusion is, in order to approximate continuous functions on these surfaces, you need 2 polynomials, not 1. You need the sum of 2. And then you may hope for an analog of the Weierstrass theorem. So that brings me to the question. Now I know that I can approximate only on the surfaces, and I need 2 polynomials. So the question is, yeah, and I'm going to look at the special domains which are star-like domains and zero-symmetric. Well, this geometry that I'm assuming is kind of natural when you deal with homogeneous polynomials. So what does it mean, star-like? Star-like means that, first of all, you have 0 inside your domain. And if your point x belongs to your domain, then this whole interval x negative x is also inside the domain. So that's a star. So it has to look something like that. That's actually a zero-symmetric star. So it's not only star-like, but by this definition, it's zero-symmetric. And since homogeneous polynomials, they have this symmetry, it's natural to look at the problem at the zero-symmetric stars. So the question is, for which zero-symmetric star-like domains K, the set HD plus HD. So this means now you're taking sums of 2 homogeneous polynomials, and we came to the conclusion that you need at least 2. So when is it true that H plus H is going to be dense in the set of all continuous functions on the boundary of K? That's the problem now that we want to look at. This is the equivalent formulation of the problem. You take any continuous function on the boundary of your domain K. You take any positive epsilon. There should exist 2 homogeneous polynomials so that f minus their sum in the uniform norm is at most epsilon. Okay, let's look at an example before we come to any conclusion. So I consider a very simple case, unit sphere. If you hope for anything good to happen, you look first at the unit sphere. If it breaks down on the unit sphere, then forget your problem, right? Because that's the nicest domain you can imagine. So it's natural to ask what happens on the unit sphere then. So unit sphere is the set of those elements in the D space, square root of the sum of squares of coordinates equals 1. This little L2 norm is 1 for those vectors. That's the unit sphere. Now, simple observation. If I take the norm of a vector x to the power j, and j is an even integer, this is how this is going to look like. Like, I had a square root, but j is even, so I'll get an expression of this form. Now, that's a homogeneous polynomial, right? Because j is even, so j over 2 is an integer. So when I raise to this integer power, I'll have a homogeneous polynomial of degree exactly j. So mod x, by mod x is the little L2 norm of x, raised to an even power j is a homogeneous polynomial of degree j. That's an important observation. Now, let me take any algebraic polynomial, not necessarily homogeneous, any polynomial. Any algebraic polynomial can be written as a sum of homogeneous polynomials. Degree n minus 1, and so on, a constant, right? I can do it to any polynomial of degree n. Now let me rewrite this sum as two sums. Into one sum, I write those homogeneous polynomials in this sum for which j and n minus j is even. That means j has the same parity as n. And into the second sum, I collect those homogeneous polynomials for which n minus j is odd. So I can split this whole sum to two sums. Now, in the first sum, look what I'm doing now. I put in this factor. Can I do this? Now, on the unit sphere, this quantity equals 1, right? So I just put in a 1. Multiplying by 1 doesn't change anything. And this is another 1. Again, multiplying by 1 doesn't change anything. So I can stick in these two factors there. Now, n minus j is even, right, in this first sum. So when n minus j is even, we already said that an even power of this quantity is a homogeneous polynomial of degree n minus j. I multiply it by a homogeneous polynomial of degree j, I'll get a homogeneous polynomial of degree n. And something similar will happen in the second sum, except that here I have to write n minus 1 minus j because n minus j was odd. Now n minus 1 minus j is again even. Repeat the argument, you can see that this sum now is a homogeneous polynomial of degree n, and this sum is a homogeneous polynomial of degree n minus 1. So what did we prove? Actually, what we proved is that on the unit sphere, all polynomials of degree at most n can be written as a homogeneous polynomial of degree n plus a homogeneous polynomial of degree n minus 1. Remember, any polynomial can be split into this sum. But on the unit sphere, forget everything else. Only the first two come into play. So this, again, this relation is true on the unit sphere. Now, by the Weierstrass theorem, polynomial of total degree n, they are dense, right, in the set of continuous functions. Then this sum has to be dense as well. It's the same thing. Therefore, HD plus HD is dense on the unit sphere. So we showed that unit sphere is fine. So on the unit sphere, we can approximate all continuous functions by sums of two homogeneous polynomials. So Weierstrass theorem, at least, is true on the unit sphere. Okay, and here is a conjecture which I proposed exactly 10 years ago now. The conjecture was that for any zero-symmetric convex body, the set H plus H is dense on the boundary of the convex set. Well, convexity means, of course, the set is convex if given any 2 points in the set. The whole interval, the whole segment connecting these 2 points belongs to your set. And this conjecture, it can be considered as the analog of the Weierstrass theorem for homogeneous polynomials. Of course, it's just a conjecture at the moment. Now, you may think that it's a little bit too courageous to propose this conjecture if all you know is that it's true on the unit sphere. Because from the unit sphere to any convex body, it's a long distance, right? Now, actually, what happened, I noticed this little observation that I showed you, that on the unit sphere it's true. And then there was one other set which I was able to settle. And that was the square in 2 variables. Unit square. By some different means, I was able to do the Weierstrass theorem on the unit square as well. Only in 2 variables. But then I was thinking, okay, sphere is good, and square is good. Now, these are like 2 opposites, right? And it should be good for every convex body. And actually, this problem came to my mind not in 2004, but in 2002, I think, or 2001. And I got so excited. I was thinking, this is such a beautiful problem. I need to solve it. And then I kept it in secret for myself for 2 years, and nothing happened. Still only the sphere and the square. So then in 2004, I thought, okay, I'll give up. And I was at some conference, and I gave a big lecture, and I presented it. Here is a conjecture. Because I thought, you know, if I couldn't do anything more than that for 2 years, then I might as well share it with other people. Okay, now at this moment, the conjecture is verified in 3 important cases. This was as a result of me sharing the conjecture. First of all, in 2 variables, when d equals 2, it's totally solved. So you have the density of h plus h in the space of continuous functions on the boundaries of convex sets in 2 variables. The second situation where it is solved is any zero-symmetric convex polytope in the D space. And finally, the third situation in which the conjecture is solved, any zero-symmetric regular convex body in the D space. Now, what does regular mean? There is an extra property here. Regularity means here is a convex body. Convex bodies have a property that if you take any point on the boundary, there is a supporting hyperplane, so that your convex body is on one side of this hyperplane. But it doesn't have to be unique. You may have 2 or many hyperplanes at a given point. Now, if it is unique, you call your convex body regular. So the conjecture is also true for the regular convex bodies. So these are the 3 cases where the conjecture is settled now. Actually, it's interesting that I mentioned that when I gave up this conjecture and I mentioned it at a conference, there was a colleague of mine sitting in the audience by name Vilmos Todik, who is a professor in Szeged, and he had this very bright student by name Peter Voryu, and that guy was only an undergraduate student, I think, at that time, and he solved the problem on the polytope, a beautiful solution, and then he also solved it in 2 variables. And then he went on to get a PhD in Princeton, and now he's a professor at Cambridge. So now, one thing to observe about this situation is that convex polytope, again, is something that is very non-smooth. That's the second class of bodies. Regular convex body, it's a smooth body in a sense. So we have a solution for non-smooth case, and we have a solution for smooth case. So it gives us hope that the conjecture must be true, because these two cases, they cover opposite situations in a way. One thing that also comes out of this third result, the third result says that you have the Weierstrass theorem for regular convex bodies. Now, what does it mean the body is not regular? It's not regular means that you have several subordinate hyperplanes at a point. But how many points can be like this, bad points? Lebesgue measure 0 on this surface. Now, since it is measure 0 set, you can show that if you replace uniform norm by the so-called LP norm, which is an integral norm, then the conjecture is going to be true, because the set of bad points has measure 0. So in this weakest sense, the Weierstrass theorem is true on any convex body if you replace the uniform norm by L2 norm, let's say, on this surface. Okay, so what happens if your domain is not convex? I had these positive statements regarding the convex situation. Here is a very typical model case of a set which might not be convex. This is the LP unit sphere. Here is the definition of the LP unit sphere. So this is the little LP norm of the vector, and it has to be equal 1. Then this is called the LP unit sphere. What is the shape of the LP unit sphere? Well, this shape is for p less than 1. When p equals 1, this is a polytope. Actually, it's a simplex, right? And when p is bigger than 1, well, it's not a simplex in classical way, but yeah, cross polytope. Yeah, thank you. P bigger than 1, it's regular. So it turns out that if you look at the little LP balls, then the density of homogeneous polynomials is going to be true if and only if the ball is convex, which means p is greater or equal than 1. So that's the statement here, that H plus H is dense in this set if and only if p is greater or equal than 1, if and only if. So now it's a necessary and sufficient condition. Now, some parts of it I already covered, because if p is greater than 1, then it's a smooth convex body, and for, regular, we called it regular. And for regular convex bodies, the conjecture was solved, it's fine. When p equals 1, that's a cross polytope. For polytopes, Warrior's result again gives us density. The nice extra information in this proposition is what happens when p is less than 1. That's when your ball is going to look like this. It's not going to be convex. You can prove that density breaks down. Actually, this last sentence here is kind of vague a little bit. What I mean to say that it can be shown that any time you have a domain which just has a little cusp like this. So if you have an almost convex domain with a little cusp, the density will break down already. So that's why it breaks down for little LP ball when p is less than 1. That's the meaning of this last sentence. Similar situation happens for the polytopes, actually. That if I just look at the class of all polytopes in the D space, zero symmetric polytopes, then H plus H is going to be dense on the boundary of the polytope if and only if this polytope is convex. So in the class of polytopes, convexity is a necessary and sufficient condition. Again, the sufficiency is the result of Vario, because he showed that density is true on the convex polytopes. The necessity is the new information here. And it turns out that an interesting thing happens here. that if you have a polytope which is not convex, let's say looks like this, zero-symmetric non-convex polytope, and you look at a function which is continuous on the boundary, and you assume that your function can be approximated by sum of two homogeneous polynomials. Let's assume that it can be approximated. Then one can show that this function, which can be approximated, has to necessarily vanish at this inner vertices of your polytope. So you cannot approximate every continuous function. This is a necessary condition in order to be able to approximate. So the density in general breaks down when the polytope is not convex. Okay, so here are the two classes of the domains, the LP unit spheres and polytopes, for which the density and convexity are just equivalent. You have density of homogeneous polynomials if and only if you are in the convex situation. And if you have a LP unit sphere with p less than 1, or you have a non-convex polytope, you don't have density in general. Now, both of these classes of sets, they are non-smooth in the sense that LP unit sphere, when p is less than 1, it looks like that. It has a cusp. And a non-convex polytope looks like that again. It has an inner cusp. So one gets a feeling maybe the fact that the density breaks down has something to do with these domains not being smooth. So the smoothness is the problem. So if you assume the domain is smooth, maybe everything will be good. Unfortunately not. Here is another statement here, which gives again a class of domains for which density breaks down. You don't have density, but these domains are not necessarily smooth. I'll explain what it means here. I introduced this quantity delta k. It is the distance from the origin to the boundary of the set divided by the radius of the largest ball which is contained in your domain. So think about a domain like this. This is the origin, okay? It has a big ball inside. This is Rk. Rk is the radius of the largest ball inside your domain. Now, this distance from the origin to the boundary is this distance here, right? That's the minimal distance between the boundary and the origin. Now, what this proposition here says, that if this ratio is less than 1/2, density breaks down. Of course, you can have a picture like this when this distance is very small compared to the radius of the largest ball which is inscribed into your domain. If this ratio is less than 1/2, it's already no density. This domain doesn't have to have cusp. It can be very smooth. It can be analytic. So it shows that the smoothness doesn't really have anything to do with the problem. Okay, next question. Can we have a density for homogeneous polynomials to be true at any non-convex set at all? Because so far all the positive results where density is true, I gave only for convex domains. Can you have a non-convex domains for which density holds? And it turns out that yes. The answer is again yes. Here is an example. Take H star to be a fixed, even homogeneous polynomial. And this L sub H star is the level surface of this polynomial. So this is the set of those points where H star equals 1. So it's the so-called level surface of a homogeneous polynomial. And I assume that this level surface is compact. It doesn't have to be a bounded set, but it's for many homogeneous polynomials, like level surface of this homogeneous polynomial is the unit sphere, right? Level surfaces of homogeneous polynomials, they can have this shape. They can have different shapes. And the statement here says that anytime you have a compact level surface, then the homogeneous polynomials are going to be dense in the set of continuous functions on this level surface. And this level surface doesn't have to be convex. So it's just an example that they may have density without convexity. So looks a little bit complicated when you try to realize what happens when you don't have convexity. You can have examples of all kinds. And here is another question. All the domains so far, everything I was saying, I always assumed zero symmetry. Zero symmetry means if you have a point x in your domain, the negative x is also in your domain. How about the domain which is not zero symmetric? Is there a Weierstrass theorem for homogeneous polynomials there? I don't know anything. I don't even have examples. I don't know if there is a non-zero symmetric convex body for which homogeneous polynomials are dense. I don't have any positive examples, and I have no negative examples. I just don't know. What would be the first domain that one tried to consider? Sphere, right? Now, if you take the sphere centered at the origin, that was my very first example, everything is fine. You shift it a little bit. It's not zero symmetric anymore. No idea what happens. I tried to shift it and I couldn't do it. Okay. Two observations which are kind of useful in this whole business of approximating by homogeneous polynomials. This was basically what Waryu did, this first observation, that if your homogeneous polynomials are dense for several convex bodies, and you take the intersection, then it's going to be fine on the intersection as well. That's how he did polytopes. Polytopes are basically finite intersections. So if the problem has a positive, if density holds on several convex bodies, then it's going to be true also on the intersection of these convex bodies. Another observation which is very useful in this area is the following statement. In order to show that h plus h is dense in the space of continuous functions, it's enough to prove a seemingly very simple thing. It is enough to show that there exists a sequence of even homogeneous polynomials which uniformly tends to one on the boundary of the set. That's all you need to show. You need to show that there exists a sequence of even homogeneous polynomials tending to 1. You don't have to approximate every continuous function. It's enough to approximate unity. Now, why is that true? This is kind of an obvious implication of the Weierstrass theorem. Let's assume that you can approximate the unity. So you have a sequence of even polynomials which are approximately equal to 1. By the Weierstrass theorem, any continuous function can be approximated by some polynomial. Not homogeneous, of course, but some polynomial will differ from your function by at most epsilon. So your function can be written as this polynomial approximately, right? This is the Weierstrass theorem. Now what I do again, I split this sum into the sum where mod k here is even and the sum where mod k is odd. And I multiply by this homogeneous polynomials of corresponding degrees 2n minus mod k, 2n minus 1 minus mod k. Now why can I do this? Because these homogeneous polynomials, they are just equal to 1. It's a similar idea, just what happened on the unit sphere. This is basically 1, right? We're assuming that you can approximate unity. So what I put in here, these extra terms, they're just equal to 1. You multiply by 1, you don't change anything. But now, mod k is even. This is homogeneous polynomial of degree 2n minus mod k. X to the k is homogeneous polynomial of degree mod k. The product is a homogeneous polynomial of degree 2n. Similarly, this sum is a homogeneous polynomial of degree 2n minus 1. You are done. So it's enough to approximate unity by even homogeneous polynomials. We had this positive resolution to the problem when the convex body was regular. Can we relax regularity a little bit? I will introduce here another property, which I will call quasi-regular. And it turns out that you can replace regularity by this quasi-regularity. And actually, when this was noticed by a colleague of mine, Vilmos Stotic, whose student was Peter Vorju, who gave some interesting results here, there was a hope that with this notion of quasi-regularity, maybe the whole problem can be settled. So what do I mean by quasi-regular? First of all, convex body is called epsilon regular if for any point on the boundary the angle between two supporting hyperplanes is at most epsilon. That's epsilon regular. Remember, regular means you have a unique hyperplane. Epsilon regular means that you may have two, but the angle here is at most epsilon between the two hyperplanes. Of course, if you have a regular convex body, it is going to be epsilon regular for any epsilon, right? So here is a definition. A zero-symmetric convex body is called quasi-regular if there exists an integer which depends only on k, such that for every positive epsilon, this k is an intersection of at most m epsilon regular convex bodies. So a thing to notice here is that integer m here is a fixed integer which depends only on k, not on epsilon. So you should have a fixed m which works for this convex body for any epsilon. And your convex body, you should be able to represent it as an intersection of at most m epsilon regular sets for any epsilon. And it turns out, and that was a theorem recently proved by Todik, that if you have a convex body k in RD, which is quasi-regular, then homogeneous polynomials are going to be dense. So you get a positive solution to the problem, not just for regular convex bodies, but also for the quasi-regular. Now, of course, all regular convex bodies are quasi-regular. So the result for regular convex bodies follows from here. But also all polytopes are quasi-regular, because a polytope is just a finite intersection of this slabs. Thank you. And slabs are regular. So again, polytopes are in this situation as well. What is more interesting, and that's kind of surprising a little bit, that if you take any zero-symmetric convex body in R2 on the plane, it is always an intersection of at most 4 epsilon regular zero-symmetric convex bodies for any epsilon. So this integer m, which we demand in the definition, in R2 you can choose m to be 4 for any convex body. So what it means that on the plane, any convex body is quasi-regular. So everything is quasi-regular on the plane. And that's why in two variables there was a complete solution to the conjecture. So basically, this nice theorem here, it didn't provide new information, but all the 3 cases which we already settled, they are all built into this one statement. And there was a hope that maybe in higher dimensions everything is quasi-regular. But unfortunately, this fact that every convex body is quasi-regular, it's true only in 2 variables. In dimension 2. In 3, it's not true anymore. If you take a cone, something like that, in 3 variables, because of this point here, it's such a bad point, it's not going to be quasi-regular. So this approach, it seemed to be very promising at the time, but turned out that still didn't help to resolve the full conjecture. Actually, as I mentioned, the cones, they are not quasi-regular, but you can settle the conjecture on the cones separately. Actually, cone has to be symmetric, because everything has to be zero symmetric, but so the cone is not a counterexample to the conjecture. It's just this approach doesn't work for the cone, but you can do something different for the cone. Well, I have about 10 more slides. I have a feeling that this is probably about enough. Because maybe, hopefully, you were able to enjoy this part, and I feel that it might not be so enjoyable after a while. So thank you for your attention.